report. Hello, everybody. So tonight's kind of an exciting night. We're a couple weeks in, about halfway through module 2 now. And what I have on the list for this evening is pretty much going to finish up what you studied in detail up through the prereqs for this course. So this finishes up the syntax, and now we're ready to get into the interesting Java stuff. Along with that, going to be a fairly short class tonight, lecture-wise. Obviously, our schedule is blocked off till 8:50, so a great time to get some practice with this stuff. After this next thing, that's pretty much going to cover what you would have seen so far through the prerequisites. I guess object-oriented stuff shows up as very briefly in SDEV 140, but for the most part, we've seen those basic tools now, and we'll be ready to jump into the more interesting Java-specific stuff. So it's going to speed up quickly. So if you're still catching up on those first couple assignments from Module 1, or I guess the stuff from this Module 2 yet, even though that's not due till next week, tonight's a great night to work on that, get caught up, make sure you're comfortable with the basic structure of the syntax, because our class examples and things are going to start, the speed's going to increase rapidly on those. But kind of an extension of what we were talking about the other day. Does anybody have any questions before we get started? I'll go ahead and pull up my notes, but yeah, this is the 4th time I've used the notes, so I know what's in them. Might have to mostly just check for the little side note written in the margin after the last time I gave the lecture. But the other day we were looking at arrays, actual arrays, because in the prereqs for this class, we use languages that don't have actual arrays anymore. That is a collection of data, collection of similar type data stored in memory locations and accessed by a recursive algorithm. Although in the modern world, that recursive algorithm is just the next spot over, just +1. Way back in the day when we used actual heating coils, that next spot over would have been a big fire risk, but that's not the case anymore, so we just go with the easy algorithm. But that one, at the beginning of the definition, similar type data, everything in an array has to be the same type. We have an array of integers, or we have an array of strings, and we can't put an integer in an array of strings. We can put the symbol there, we could put something that would look the same when it printed to the screen, but if we stuck, say, the number 3 there, we had an array of strings and stuck a 3 there, we'd have ASCII or Unicode number, 48, 49, ASCII number 50, or Unicode number 50, not the number 3 that we could do math with. So we can't mix our types. That's why you wouldn't have seen an array in an actual array in the prereqs for this class, even though we call it. The structure we used there was kind of nice though, because it wasn't, it was, in those prereqs, the things that we were calling arrays were dynamic. We put a bunch of stuff in there. If we wanted to add more, we just add more to it, take things out. Our size would grow and shrink as needed, which is a very convenient thing to work with. And that's the next one to look at in our list tonight. I almost said that word, just the normal English word, and that's actual lists, which we usually use the word array because lists has a lot of normal everyday uses in English. I had to very carefully avoid it in the introduction here, and I think I still might have said it a time or two, because it's just a common word, so we don't want to misinterpret what a list is as far as a data structure with all the things that a list is in normal everyday life, because there's not really a lot of overlap there. But lists have a lot of advantages to working with as far as the data structure. And we kind of They're a little bit more common. Arrays will be faster because the computer does not have to spend time figuring out what type of data we have, how much space it needs to store it, or adjusting when we want to, because we want a dynamic collection instead of a fixed size collection. The computer doesn't have to waste any resources on that because we, the developers, did that before even compiling the program to begin with. So we get a lot more speed out of an array, but at least for anything in the classroom, that more speed would be in the nanosecond range, maybe milliseconds if on your big final project. But when you're in like big settings, right, where you're working for some company, you're dealing with software that's going to do it, we're going to deliver 400,000 ads every second. Then those nanoseconds make a bigger difference. So again, that point to just keep in mind that classrooms have such tight time constraints. Everything we do here has to be designed to fit into our time constraints. And when you graduate and start looking for jobs and start working, the world at large has moved on to much larger problems that could possibly fit in a classroom. I think everybody was probably already aware of that, right? Just making sure that's explicitly stated, because even if it's in the back of your mind, I've seen it take people by surprise when they start job hunting, find jobs and get their first couple assignments after getting the software development degree. It's like, wow, that escalates quickly between graduation and day one on the job, because on the job, you're not under the time constraints. You're under the get the job finished constraints. However long it takes in the world is, after 80 years of computers, software development at large has moved on to much, much bigger problems than we could possibly hope to fit in the classroom. So back to our topic tonight, lists. So we drew the picture. I'll use stack heap diagram. The definition of a list written down. Somewhere in my notes, probably have the formal definition. I'll do it with a picture. The formal definition is definitely in the book. So back to this picture that I like to draw. And when I'm working on big problems, think about what's going on, connect the code to the RAM, and there's extensions on this picture. Sometimes I'll extend it even further and like draw some stickment around it, make a whole use case diagram. When trying to track down those big problems, we're sitting there changing words in the text file just isn't enough to make the program run. Like the entire logic algorithm structure has to be revamped. Those sort of problems. Pictures come in a lot more useful there, but if you go ahead and sketch them out in the classroom, you get some practice with them and see how to do it in easy settings. I'm going to make that point about planning. Anything that fits in the time constraints of a classroom, I will definitely agree could be handled without a plan. You can sit down and start writing the code. It was designed to fit in a classroom, so it's designed to be small enough to solve it as a weekly homework assignment. But the parts of a plan, just jot down some notes. I'm going to talk about that this semester, so let me do this little side step. And when we go to make a project and deliver that, we're going to do a big fancy project proposal, right? We're going to sit down, think about what needs to be made, and write up some fancy proposal. Put it in a really nice document, all sorts of images and fancy eye-catching graphics to get people's attention, charts and graphs, and write-ups of what we're going to do, and descriptions of what the software is going to accomplish, and all of those details, just pages and pages and pages of them. But there's only 2 lines people care about. The budget and the timeline. And we can't abbreviate it to just those 2 lines. We have to turn in that whole proposal. But all the customers and the managers are really going to care about are those 2 lines. how much does it cost and when do they get it? And the thing about the classroom, especially with that planning stuff, is in the classroom, those two lines are as trivial as can be, right? Students, so the budget's pretty much always going to be 0. And the timeline is the due date. Utterly trivial in a classroom, but when you get out to the real world and that big fancy project proposal, those are the only 2 lines your customers and managers are going to care about. So you can get some practice with that in a classroom. Just make up some numbers. Like instead of those trivial ones, just when you sit down to make a project, you're like, okay, I think this is going to take about 45 minutes. 45 minutes, and I'm charged $60 an hour. Just making up numbers, right? So like 60 per hour times 3/4 of an hour is what, $45. You get you some numbers to write down. Maybe the first ones are just a complete arbitrary guess. But then after you make the plan and go ahead and write out some of the other lines in the proposal, like what the algorithm is going to be, and practice on the easy stuff, because if it's easy enough to do it without a plan, then it's obviously going to be really, really easy to make a plan for it. You don't want to learn to make a plan when you need the plan. So you'll have those details kind of worked out, just a quick sketch. And then afterwards, come back and look and like, oh, well, I was way off. That took an hour and a half to make. And since the budget, the money was based entirely off the time, that was way under. And after you do that a few times, you'll get better and better at predicting how long it's going to take to do something and how much it's going to cost to do it. And if you're really good at predicting those 2 lines on the proposal that your clients and managers actually care about, they will notice that very, very quickly. When customers, when you come in on time and at budget, not necessarily ahead of time and under budget, those ones that sound really good, but just deliver it at the time you said you would for the amount you said it was going to cost, they're going to be really, really happy. They're going to tell everybody they know about it. Your managers are going to take notice of that. It's going to come into play come yearly review, getting ready for raises and stuff. So it is well worth the time to get some practice with those numbers and practice on the plans, even though anything that fits in a classroom we could easily do without that part, right? We could skip over it, but we're in a learning situation, so make sure you're learning things productively, things that will be very, very useful when you're out there working. Because those numbers are the ones that will make people happy. If you're good at predicting those, people will definitely notice very, very quickly, because a lot of people are not good at predicting those numbers. And the only way to get good at predicting them is to practice. First ones are probably just going to be a guess. Just take a guess how long it's going to take and how much you think it would cost to do that. And afterwards, take a moment to look back at those numbers and see how far off you are. And that way your next guess is better. And then the following time it gets better and better and better. And the first one's a random guess, but then it becomes an educated guess and more of an educated guess part. So that the prediction gets accurate, and that will make a difference for you in the long run. And it's really, really easy to practice on your homework assignment, right? Like, how long would it take to write that down for some of the weekly chapter programming exercises? 5 minutes, maybe, if even 5 minutes. Doesn't take long at all, and the practice will definitely pay off in the long run when you get to a bunch of bigger stuff. Okay, so back to our stuff. So what a list is it's a collection. Instead of that rigid structure that we have with an array, where I'll draw them both on here in colors because it looks like the black marker is about to give out on. I'll do the array in blue. So we saw the other day with an array, we declare it, and then when we define it, means we're actually putting some values in, ready to use it. It follows that strict structural rules. I guess I can put it in here. An array with 3 elements just because I don't have much room on the board here. And that's what it gives us. In Java, we just use the next one over. And we reserve that chunk of memory for the data we want to store. And that's what we have. If we suddenly realize we have a fourth thing we meant to store there, the only option we have is to create a bigger array, copy everything over, and then add that fourth item in there. So quite a bit to copy to adjusting that. A list is a much more dynamic structure. So right off the bat, we don't have to say what we have. And I was careful a few times in the lecture, you probably might not have picked up on it. For one of those subtle things, after my marker just suddenly disappeared. I was careful to explicitly say declaring the array versus defining the array separately. We can set aside the spot in memory, say we have an array and not put anything there until later. A list, as soon as we declare it, we do have something in memory. That reference comes with our list. It's pointing right at the first element in the list, even if there's nothing in the list. Here in a second, we'll see why that's important. But when we start putting elements in there, maybe the same 3 data points. What I put there, 1, 2, 3, 4. Yeah, we'll have the same data. So we have our first one. Then instead of just an algorithm to decide where the next one goes in RAM, we add a little bit extra data that serves as a pointer to the next element in the list. So this little bit at the end, maybe it points over here in RAM. And there's our next element stored there. We'll add just a little bit extra data for a pointer. Point over at the next element. And at the end of the list, we end up with a null pointer. It doesn't point at anything. Electrically, it's the pointer that just goes back, feeds back to ground. Any electricity that heads down that pathway just filters itself back to ground, basically. But when programming, we call that the null pointer, the one that's just pointing in open space. It's not pointing at anything. And that gives us a lot more dynamic structure. That's why we had that initial reference. And the way it's described at this point, that probably sounds fancy. Like add a little bit extra data with the pointer. That's one data field. Transitioning still between variable and data fields. Object-oriented specific, you think of it as a variable still, we're only in module 2. When we set up an object to represent the things in our list, we just add one more variable in there that says next. And as long as that next variable holds something, we are still in our list. And when we get to the end, there's nothing in that variable. That's how we can tell we're at the end of the list. So a really, really easy thing when we get to coding it, which I think is week 11-ish, somewhere around there, past the middle, around November, we'll be getting into that. It's not too far off, but we're going to look at a bunch of data structures. It sounds fancy here, but that's just one more data field we put in there. We just create a data field called next, and then that we put whatever the next item is on the list, which is what gives us our dynamic structure. So unlike the array, if we had suddenly realized we have a fourth item, well, we have to make a new array to do that because our array only hosts 3 things. But over here, well, we can just have that last pointer point over at another element, put a new element at the end of the list, and then its pointer goes off into empty space. Is the null pointer. So we can extend those indefinitely. Maybe we don't need this one anymore. To get rid of it, all we have to do, put down another color. We don't want this one. All we have to do is stop pointing at it. We can leave it there in RAM and just get rid of that, take that pointer and make that pointer point at the next element. And then our list is a little shorter. And garbage collection will grab that soon. In C++, we'd actually have to go through and clean that up. Java has really, really nice garbage collection. So as soon as it notices, every few milliseconds when it makes its pass, it notices that, oh, there's nothing that points to this element in the list. There's no possible way to get to it. It'll clear it out of RAM for us. So with a list, if we need to take things out, all we have to do is stop pointing at them. If we need to add more things, we just point at something else. So that pointer gives us that dynamic structure. That's the type of data, that's the data structure collection that we use most often in Perl and Python. That's pretty much what we have in both of those languages. Everything else is going to be built out of a list. And those are both open type languages. I mentioned Perl, probably thinking, I haven't seen Perl. If you use Raptor in SDEV 120, that was written in Perl. So what we drag around the pictures on the flowchart, and then it writes some Perl code in the background, and that's what runs. It follows the syntax and it follows the structure of the Perl programming language. Even though you probably haven't actually seen that one, it's not as common as it once was. At least you've used it, it was just automatically typed up in the background. Most of y'all have probably used it. I think most of the classes are still using that. But in those languages, they're also open type, so we don't have to worry about type. In Java, we will have that type restriction. So we have to say that we're working with a list of integers and only put integers in there, or a list of strings. There's a workaround to it because it's an object-oriented language. So somewhere way up that chain of inheritance polymorphism is like that master object. It's actually called object. We'll talk about that soon. So it can just always say that we have object data because anything we use in Java is a subclass of object data. It's probably 10 or 12 subclasses down at least from actual object, but there's a lot of stuff that work in there we want to use, but we can kind of treat it like that. But in general, this is the sort of data structure you would have used in your last class. There are two main ones we will use. We're going to look at more later. We'll probably look at more when we're looking at data structures, but there are more lists we could look at, but there's a lot of data structures that we have to squeeze into a short period of time. And the other lists are just finer details of what's going on in that list. They're still just basic lists. The ones we're going to use most often are ArrayList and I'm going to put this little symbol here in angle brackets. I'm going to put a T. I think our book likes to use an E for that. We're in a strictly typed language. We always have to say what type of data we have. But when they created an array list, they had no idea what sort of data we would want to put in there. So they had to put in a placeholder. We call those generics, which I think are in next week's to-do list. So we will see those very soon. If they're not in next week's, they're in the week after's. So we're not far away from seeing that, but it's a placeholder. When they wrote the code for this object, they had no idea what we wanted to put in there, so they put a placeholder. When I learned it, I always used the letter T for type. I think our book likes to use E for, I think it stands for element. I'm not completely sure what E stands for. It's very common. T and E are the most common things to see there. But those are just placeholders, so it doesn't matter what's there. It's like a variable. We can call the variable whatever we want. It's the data that's inside that variable is holding that actually matters. There's also linked list. And again, we're in a strictly typed language, so we have to fill in that generic type. They left that generic placeholder, and when we go to use it, we have to put something in that placeholder. So linked list is directly what I drew the picture of here. There's also a doubly linked list, which a lot of people like, that along with that pointer, which is just a data field that says next and has a reference to the next item in the list. We could also add in a data field that says previous, or we can call it whatever we want. Most people just call it previous, which gives us another arrow, another little reference value pointing at the previous thing in the list. And that way, when we walk through the list, start at the beginning, walk through checking all our elements to see if that's the one we want, we can go both ways. We don't have to go just one way. That's a double linked list, which Java spells everything out. So just put the word double at the beginning if you want the two-way pointers. In general tonight, though, I'm going to point at linked list. So that picture I drew in red there is a linked list, and an array list is, we're going to talk about some finer details yet, because we don't have all we don't have all the details just yet to talk about it. But it's basically a linked list of arrays. And the thing I mentioned, where if we need more, we'd have to make a copy, move everything over, and then adjust that. All of that is handled automatically in the background. So we have a list, and it just keeps pointing at things. In particular, we're not room there, so I'll draw another stack heap diagram. Yeah, I'm still on video. So our array list, I'll write something like that, half abbreviate it. So instead of pointing at one element, it creates an array. So at first, it creates an array with 8 elements. And then it'll start putting things in there. So when we start adding things to that list, it's going to start putting them in that array. And when that's 3/4 full, 75% full, it's going to do the little list pointer thing at the end of that array that holds 8 elements and point at another array that holds 16 elements. Then it'll finish filling up that last quarter here, move over to this one, and when that's 3/4 of the way full, it'll automatically add that little pointer and repeat the process with 32 elements. You all see where that pattern is going. So it grows very, very quick, right? 3/4 of 8 is 6. So if we need to store 7 elements, we've actually reserved enough spot in memory to store 24. So there is that wasted value there. So it's not going to be as fast as our regular array. And we have a bunch of extra RAM that we're using unnecessarily to store that 7th element. But when we don't know how many elements we have at the time we're writing our code, and it's going to grow and shrink differently, that's a whole lot easier to work with. So it combines an array and a list. It gives us a list of these non-dynamic data structures that automatically extend themselves as we need them. And if we start taking things out of the list, we have to get all the way back to this add point. So if we put 3/4 of that's 12, so 8 and 12, we get up to 20, put our 22nd thing there. It's going to create that other one. And we keep adding things, get up to 40 something elements, we're way up here. And then we start taking them out. It's like, okay, we're done with those things. We start removing them from the list. It's going to come back down. And it's all the way back down to 8 plus this 8 full plus 12 of these before it deletes that space. So the add and delete space is at 75% full on the next one. It follows patterns to do. We start with 8 elements. If we need more, we get enough space to hold 16 elements on top of those 8. We need more, 30 gives us space to hold 32 elements. Then 64 elements, then 128 elements, and I think you'll hopefully see where that pattern is going. Anything in these notes? Let's just talk about comparators. So that's for when we get into the data structure lecture in a couple weeks. For now, I'm just finishing out our basic syntax with something that will behave like what you used in previous classes. So I want to make sure there's plenty of time to do stuff tonight so that we can get some practice. It's an active subject we learn by doing. So some great practice is now that you've seen all those pieces you would have used in the prerequisites for this class, you should be able to remake any of the things you did there in Java to get a little bit of practice in Java. The syntax before we get into, now that we're ready to move into the Java specific stuff. Any questions about that? Y'all ready to see the syntax? So we can do stuff. Get to the doing stuff part. I'll open up NetBeans and start a new project. New project. I was going with a regular project. Should I do that? I haven't done a Maven project. I'll go ahead and do a Maven project this time. The difference is all going to be in the foreground, and I didn't plan on a lot of stuff to pop so that we can look at a couple things like here and see some of the differences. Actually, I'm going to create a Java application. If I'm going to do that, I'm going to point at both of them. So I'm going to create a Java application and a Maven application, and then use the Maven one this time because we haven't used one of those yet. Maven Java application next. You'll see it's basically the same sort of stuff. What's the project going to be called? Who's making it? Group ID. This will come in handy later. You see by default, it kind of looks like somebody's website backwards. Instead of mycompany.com, it's com.mycompany. There's some patterns worked into. We're not going to see on day one of looking at it. We'll see what version numbers are working from the beginning, and then we have the package. You notice the package is a little bit longer. We talk about packages. That's basic. The starting point on that is that's the folder we put our source code in, how we organize it. And then our very first line has to refer to what package that source code is part of. And you'll notice that it has this name, and then something generated that seems to go with the project. So there's a whole bunch of folders going down to it, which is actually much, much better for the computer. As a human, we don't see that because when we have a whole bunch of folders to dig through to get to any files, that means a whole lot of double clicking, right? You have to double click on something, and then the only thing in there is another folder. So we have to double click again. Then we get to another folder, double click again, and eventually we get down to just a single file. That's much, much better for the computer. It doesn't seem like it whenever we're clicking our way through the files, but that structure is much better for the computer. So that's one of the differences. The packaging, all the automated processes are set up for the computer format instead of the human format when we use the Maven project management packaging solution. But you'll see it generated something, a very similar looking template to what we had over here. These comments at the top we gotta get rid of, they're just in the way. The very first line has to be the package name, so obviously that's different between the two of them. They tried to put in some Java docs, and then we're down to our public class with the main method in it. And just in case I haven't explicitly stated it enough for a couple weeks or overlooked explicitly stating that, all of your code that does stuff has to be inside of a method. You can do declarations outside of the method. Like you can say, I have an integer, it's going to be 4, but then you can't do anything with it. All you can do is declare it outside of a method. If you want to do anything, it has to be inside a method. And we started the main method, so you can see after I get all that generated stuff out, the only difference between those two is the package name. Well, I guess, and the template says start with the to-do comment, and the Maven project goes ahead and does the hello world, so we can do a check. Which, another big difference here, I'll go ahead and run this before we get into our code. And talk about the Maven stuff first. You're much more likely to use Maven packaging. I just wanted to start with AMP because that is in human form, so it there's a lot more going on with it. Actually, let me copy this. I'll have both of them do the same thing. I'll replace the to-do comment over here with that, and then run this one. Okay, so you can see on the AMP project, it said, okay, run it. So the words hello world come out, spit out, and it says our build was successful. On our Maven project, well, we had that at the end. Is the scroll bar showing up on there? But you'll notice over here on the right, the scroll bar is a little bit bigger on the Maven project. The AMP one didn't even get a scroll bar. Because before it did all that, had to check everything out, look at what version it's using, check that. Oh, it noticed a change, so it adjusted things. Oh, then executed it. I was expecting one more thing. I was expecting it to go out to the internet and check the central repository to make sure all the libraries were up to date. Maven will do that almost every single time. So when you're compiling and debugging your project, it will take a lot longer for every single run because it might need to take 45 seconds or so to run out to the internet and check every single Java library in existence to see if any of those have been updated since the last time you hit the run button. Hopefully you can see the big advantage to that immediately, right? Everything's centralized. There's this Apache runs a central repository that everything is up to the date. And when you click that green button to run your code, it will check for the up to the millisecond up to date for what you're doing. So a lot of advantages to it, but there's a lot more going on. So you can see a lot more going on, but essentially we get the same output in the end. And most of that, all of that is going to show up at compiling and debugging. And while we're putting it together, once we release the software, the end user won't be able to tell what we made it with. There's some other things. You can see the folders are very similar. We have some source packages, then we have more folders along the way. There's nothing but more folders in there, so NetBeans just condenses those all to one. If I come over to File Explorer here, and NetBeans project. So here's the AMP project. Right there's our source folder, and then one folder deep is the package itself. In the Maven project, the source, target, and the POM file, we'll look at that here in just a second. In the source, there's another folder called main, and then that has a folder called Java. And this is what I was talking about. This is better for a computer, but It doesn't seem like it when we're just clicking our way through folders that don't have anything in them but one more folder. Okay, now we're down to something that was actually listed in the IDE. We're down to com.mycompany. If you haven't seen that before, in your code, the dot is like the slash in the addresses, what you would normally think of as URL, right? C drive slash user folders slash username slash documents. If we need that in our code, we would put c.user.username. And you've probably seen it and didn't necessarily know what it was, but I think everybody's also in here's also seen enough code to kind of have a different perspective of directories now, right? So where do we normally use the dot? That's what the directory structures really are when we're working on. Those are objects. Those are objects that belong to other objects. So that's why we have to use the dot when we get there. Okay, yeah, and then eventually we'll get down to down to our source code. So it's way deep in folders, which is better for the computer. It's an automated process. That should probably be better. And you see there's a long list here to get back up to the dot. All the folders we had to go through won't even show up in the address bar. But there is an advantage to that. Then we have dependencies. There's none here. We're not depending on anything. Which development kit we're working on. Come up to libraries. See, it's the same development kit. Here's the libraries we have available. We haven't done anything special. We'll see using our own libraries before long. But the same stuff, it's just packaged a little bit different, organized different. And a couple other big different things. I just noticed, see my IDE doing something automatically. So unpacking index for central repository. Since all I did was hit run on that default version, it knew there was nothing to check, so it just checked. Apparently went and checked it afterwards in the background. So it'll run a little bit quicker. I'm going to stop that because I wanted it to happen when the code runs, so y'all can see all that stuff flash by on the output. We will see that here shortly. Source code. So for our packaging, those automated processes over in Antwin, we have our build instructions and the manifest. I open those up with Sublime. It's probably easier to go and do Sublime here. Open file. Document. So in Ant, the manifest is generated at runtime. If you haven't dealt with those yet, we'll talk about those soon. Some classes that whether they're not automatically generated like they are in pretty much all of our Java packaging, I started working those in a lot more. Manifest is just like we would use that word traditionally, as far as like a ship's manifest. That's the list the captain has of everything that's on his boat and why it's on his boat or her boat. Why it's on the captain's boat, everything on the captain's boat and why it's on the captain's boat. The full extension. So we have a similar thing in our software. Everything that is used in this piece of software and why it's there. But it's the tedious sort of typing that a computer can easily put that list together for us. Kind of like drawing UML class diagrams or ERDs for a database. We can draw it, and in some of your classes, you probably were assigned the task of drawing that repeatedly, but there's no thought involved in drawing those pictures. A computer can draw those all day long, and then the human just has to organize it. You have a bunch of UML class diagrams that are all connected. It's a little bit harder to organize those on a page where you can follow. Or same thing for a big complicated database. You have a bunch of ERDs with all the connections, the full normalization, and all of that. It can get a little complicated to follow it. So a human needs to organize that so that it makes sense, but a computer can draw the picture. There's no thought in drawing the initial picture, just in organizing. So over here we have our build file, the instructions to build it, and XML extensible markup language. It's a common markup language. I think most people have probably seen those now. Oh yeah, we've been using JSP, so we've at least seen the markup languages in our small JSP examples with HTML. Tags have some advantages. It is not a coincidence. It is the exact opposite of coincidence that this symbol I put here that means generic in our C family of languages is what we use for tags in our markup language. That is the exact opposite of coincidence. Markup languages are full of type definitions. Thought I would point at that while there's one drawn on the board. But we have all the tags, and it's a whole lot easier when the computer types the tags for us. Which, as software developers, we're the ones that have to do it that one time. We have to write the text file with all those tags, and the computer will do it millions of times for everybody else. But it's not hard. It's just like writing anything else to a text file. Giving it the pretty print is harder than getting the tags in there. The pretty print is line breaks and indenting, because the computer doesn't need that. That's totally for you. But all the instructions on what to do. What to do before initializing the style. What do we do after we compile it? What do we do before a compile when it's explicitly a test run, not an actual run of the software? All of those instructions are already fed in there. You can see there's quite a bit there. It's just a markup language, so we can adjust that as needed. When we actually release our software, this line right here will get uncommented in the build file automatically. And then in the Maven project, instead of that, we have the POM file. And I just looked up what that represents. I'm going to Google that real quick because I forgot what it means. What does POM stand for? Project something. Nope. POM stand for maybe. I just looked it up so I could tell you all. And project object model. Hopefully it might sound familiar for those who've had the HTML classes or any of the web development classes with our document object model. So our project object model, it ties everything together. One central location, and you'll see it's also written in XML. So we throw in the tags. If we need another library, we just add it right in there. We just make a dependency tag. Let's see, / dependency, and maybe we need JavaFX. We'll see that before long. OpenFX. We need to depend on the OpenFX library and then URL to where that is. So we can just add those XML tags in, no problem at all. We need to add more stuff. The computer will handle all those automated processes. I wanted to look at that because that's a big deal. We kind of saw in that very quickly there, in the build file of the ANT version, we saw where we can all those feed in more specific instructions. What do we do before we compile it? What do we do after we compile it and before we run it? How do we change that if we're doing unit tests and things like that? All the instructions we need to run our program. That seems like a good first pass at Maven. We'll look at those in a little bit of detail. And Gradle is the opposite of Maven. Maven is set up with one centralized location. Maven is distributed. Gradle is distributed. The short version I always like to summarize it with is you think of on a big project, if you do it with Maven, you'll have one build file, that POM, one build file that has 1,000 lines in it. If you do the same project in Gradle, you'll have 1,000 files that all have one line each. One of those is much, much better for a traditional spinning disk drive, and the other one's going to be much, much better for a solid state drive. So those two are the ones you will probably use most often in the classroom, and it's a nice way to keep it easy. What I wanted to start with, we're gonna look at them repeatedly throughout the semester and work in more and more details, so y'all have a pretty good understanding of those. Because you've already seen some programming, you just need the syntax for Java, right? So, these next two things, array lists are, a lot of people like these a little bit better than regular arrays. If that extra space isn't going to be an issue, then we have essentially a dynamic array we can work with. So we say we have an array list, and then the type of data we have in there. Did integers last time, so let's do strings this time to start with. So we have an array list filled with strings. We need some sort of name for it. I'll use that half abbreviation I put on the board. And following Java syntax, that's going to be a new something, right? You'll probably already guess that part. Hopefully you already guessed that part. It's going to be a new array list. We need our angle brackets again, then parentheses, is this one's a constructor. And on this side, if it's obvious what that's going to be, like obvious that enough that a mindless machine can figure it out, you don't have to put the type on both sides. We're going to make an array list of strings. So obviously when we create a new one, it's going to be strings on this side as well. So we don't have to type it. That'll come into play a lot more when we do maps and caches, and we might have different things on each side. Maybe we're going to do a map so that our code, we're always typing, we'll treat it like a dictionary and use strings to index all our elements. That's probably the most common type of mapping. But on the background, we're going to do it all as a hash table. So on the foreground, for what we're typing in our text files, our type would be string and integers. And on the background, our type would be integers and longs. Because what we do in our code is going to be different than what happens in the background. So if they're different, we have to type something on both sides. For our array list, there's only one type, so it's pretty much always going to be the same. And then we need to import that. Control-Shift-I is the easy way to do that. And you'll notice that is in a library that we've already used a few times. So that comes from our java.util package. It's one of our basic utilities. Then we have some methods that we can do things with. Obviously, the first thing we want to do is put some stuff in here, right? So that'll be adding our add method. So we'll use our reference, array list, dot, and here's our list. Hopefully y'all have started trying to figure out what you need from the list. Java is really nice like that because everything's spelled out, follow those conventions. So it's a lot easier to find it on our list than some of our other programming languages where everybody just kind of did their own thing. So right off the bat, we have add. We have a couple adds. We can just add a string. We said our type was string. So once we said that, we're restricted to that type of data, like we are everywhere in Java. So our predictive text also updated and shows the add string method. Doesn't bother to show us the overloaded add double method or add custom object method. That will adapt to whatever you're holding. But the second one, notice an integer and the element. We'll use that one here in a second. Let's start with just that basic one. So we'll add a string. I'll just do hello world again. ArrList dot add world. Get those basics in there. I'll add a few more words. Add more words. Spell things correctly and add a rather long string compared to the others. Arbitrary data. I was just making that up as well. We can add things to that list. We started with an empty list. We didn't have to say how big it was like we did the other day when we looked at arrays. We just started with an empty list and added a bunch of stuff to it, which is probably what you're more familiar with from previous classes. We start with empty one and add stuff. Right off the bat, I'm going to print this. We'll go ahead and print that list out. I wanted to show you this. I'm also going to make the output window bigger. Close that one. So now when I run, oh, it didn't update it. I'm in the wrong one. Whoops, I'm in the wrong one. Not good to have multiple things over. So I'm going to cut all of that and paste it over here so I don't go to the wrong one again. Because I wanted to be using that. Oh, and that's a nice little feature in IDE. Notice that automatic insert the library, import the libraries showed up with the copy and paste. So to get things like that, make sure you're using those tools a lot of times where you could do it with the keyboard instead, because it's very, very useful. Okay, this is the one I wanted to run, the Maven project. So we hadn't seen that. So I hit run. It took a lot longer than the other one. I guess that was kind of good to see how quick the other one ran. I didn't really have to go check for anything. All the libraries were local. But we have a lot more going on than just saying we're running that project. And that list will get really, really long sometimes. Actually, pretty quick. The list will get really, really long, and it'll go out and check the central repository, so you'll have to wait on that. But a few seconds if you have something huge to deal with. And this one, notice all I did was say print the list, printed the reference, not any index or anything. And it printed it out with angle bracket or with square brackets at the end. That always struck me as that's what I would expect an array to print if we just printed the array reference. You might remember from the other day that it was different. So we can just print the whole list and see it built in. And there's a lot of those built-in methods that we have to work with. We saw the predictive text for ArrayList Java. Remember to check the official documentation. That one should always be right near the list and the tutorials. A long description of them. And then we have lots of methods. So add, the one we just saw. Oh, it looks like they use E here too. The type parameter, the generic one, because they had to put a placeholder in there when we did that. But notice in our code, as soon as we said we had a string, that predictive text automatically filled that E in. It filled in that placeholder. You can add things in a particular index. We can add an entire collection. We have a bunch of stuff are stored in another list or an array or something. We can add an entire array at once because we're dealing with a bunch of arrays. We have multiple ways to add a bunch of things at once. Clear removes everything. Obviously, can be useful at times. Looks like for each is built in here as its own method. That's a really useful. When we saw the basic for each loop the other day, when I get back over to the IDE, I'm going to do the regular for each loop. Actually, I'll do all three of them. I'll do the traditional basic for loop, a for each loop, and then we have a built-in one. But look at that type. We haven't seen anything like that, right? Consumer. That sounds very different than anything we've talked about so far. You know, our indexes, check if it's empty or not. You all can read the list, but make sure you read the list from here when you go while you're learning it. We're in a learning environment, so we'll make sure we're learning properly. Just real quick, I'll use the other add method, ArrayList dot add. This time I'll do an index 0, 1. I'll say add index number 2. Addendum. I can't think of any words quick enough, so just add in a word that means add stuff. And when we run that, you'll see it, that just adds it at a particular spot in our list. That can be very useful at times as well, because we want to worry about the order. Or if you want to worry about the order, go through in a for loop and make sure you're adding them at the right spot. So we saw we can just print it. I'll just comment that out. Whoops, I don't need to do that. I just do a regular comment. It's only one line. And then it's a collection. So just like we did with the other arrays, we want to walk through it. And when choosing between our loops, we know how big the array is going to be, or at least the CPU will know how big the array is when you go come runtime. So that's when we would usually choose a for loop, when we know the size. So for some integer, I'll just call it I, start at 0. I is less than ArrayList dot. And the other day we saw length, which was just a data field, and I kind of pointed at it, said that was a problem. You'll notice it underlines that immediately. Array lists follow our normal structure where our data fields are kept private. So if we want them, we have to go in through a method, through a getter method, which here is a method called size. That's one that's different in every language. What's that underlined? Oh, it's yellow. Okay, I just saw the underlining. It's underlined in yellow, so one we can ignore, but it's already popping up. It's like there's enhanced for loops. You can work with ArrayList instead of the traditional ones. Sometimes they're nice. If I have to put some complex selection structures in there, I usually find personally I would rather work with the index directly. Is when I would do the traditional for loop instead of a for each loop. But then we can do things like, for example, I'll keep it trivial. Next item in the list is plus the reference to the list, and we can't just access them directly. Direct access would be like that policy of our data should be held private, and the methods to access that data are what's public. So instead of direct indexing, we want to use the get method. Is that behind the pictures? It's behind the pictures on the TVA. TV's in here. We move those out of the way. So our get method, where you can see from the list there, let me put it back on the list. Get and just what index. So instead of indexing through square brackets, we index from a method. Which at this point, with what you would have seen in the prerequisites, is going to seem strange. But as you work more with programming languages where we have that fine-grained control for really big things, Java and C#, which was modeled after Java. C# is like the cleanup work they did on Java to C++, plus a lot of the advantages we had from Visual Basic. Because that was Microsoft's original language that Microsoft did all their early work in. So they wanted to use that. But that follows a lot of the same policies. Our data is kept private. So we have the objects, we use methods to get to it instead of direct access. Index it from the get method, which that's just going to print things out. So I'll just do all three of them. I'll just print it out with, oh, I better print the line. I'll print it out with line breaks, and then I'll print out a long line to separate things. Maybe a couple line feeds there. Oops. Everybody's seen that before, right? The line feed, escape sequence, \n, it's actually part of regular expressions. So that if we want to look for line feeds in something, but we can type it directly into our code as well. \t is a very useful one as well. That's the tab. Yeah, I'll do that. \n, \t, so you can see the tab go over. There's a backspace as well. I guess we'd have to, if you want to sit, I'll print it out. If you want to count the asterisks, I just held that down for a second. If you want to count them, you'll see that one of them will disappear when we print that line. Because there's a backspace character, because again, it's for regular expressions. Those are for searches, but we can type them directly if we need to. \s is a space. Some people like to do that because then we have something we can see in our code. Instead of looking for a space, looking for that emptiness, we can actually see the escape sequence for a space. So we have a bunch of those, and I'll use the other type of loop. You don't see that? I just realized it's small. I'm going to make that bigger. I'll go over here, change the font to okay. 24. Oh, that's what we're doing. 18. There we go. Maybe y'all can see that a little bit better. I know everybody has different size screens. Hope it wasn't too small. Oh. I don't know why NetBeans has been doing that to me. That seems like a little bug in there. Every time I change the font setting, that box just keeps coming back up for a few seconds. Then we saw built some for each loops the other day. Say for. Then we need to come up with a reference for our elements. So we have a bunch of string data. So for some data of string type, we'll call it, I'll call it I again, just for comparison to the previous one. Up here, index or integer, or maybe E for element. String, some string element, and then the colon is like in. I always read that as the word in. So like for each string in that array list we have. And then that'll loop through kind of the same way. I'll just copy that line from above to keep the try to minimize clutter in the examples. And that way we're looking at the same thing and we see hopefully see just the same syntax. Which that's bothered. I'll go ahead and spell that out for each element in our list. Oh, we have some nice words for our syntax examples. But that's just a variable, whatever you want to call it. And then we have that to use directly. For each pass through the list, we just call it element or E or I or whatever you feel like calling it. Probably have something useful in actual situations. But those two loops will do essentially the same thing. With an array list, this one is a little bit better, a little bit more. It's a little bit more efficient to use that one. But array list and linked list, when we look at those, after a quick break, after this next one to type here, we have a for each loop built in. So we can call that reference to our list and then dot a for each method. It's going to look a little bit different. I just wanted to go ahead and introduce these pretty quickly. I'm going to call it E for element here. That's why I suddenly decided I should spell it out. So it's most often, it's fairly a lot more common to spell it out in this type of for each loop and abbreviate it in these other two types of loops. So I'm going to call E for each element. Then we have a lambda. We'll talk about lambdas more before long. That's something that goes all the way back to 1959. Basically, it means wait. It means don't run this instruction as soon as you see the code compiler. As soon as you see the code, don't run it. It means wait for a certain thing to happen. But they use an arrow for lambdas in Java. Well, build an arrow, dash, angle bracket. So, and then notice our curly braces are being passed into that method as a parameter. So all the stuff that's going to happen happens there, but that's going to be a mess if we type that in one line, right? So make sure your semicolon's there. That's an easy one to miss because we are typing one line. It's just, there's curly braces, so there's an entire block of instructions inside of that one line. So if we did it all in one line in the text file, it's going to be a mess. So don't forget that semicolon, and then just hit enter to give yourself some space to type. And then whatever you want to do. So I'll just print out the same thing for each thing. We're going to print out the E. So does everybody see kind of what's common between all three of those loops? And not just that we were doing the same, not just that we're printing out the same sentence, but how we set up like index or actual reference to each element individually, and then kind of block out what the instructions are going to have. There's a lot of commonality. After you do some non-trivial examples, it'll probably make what I want you to see there will fit in a little bit better. Oh, I forgot to put the other one of those things. You see there's those escape sequence line breaks. If you count those asterisks, one of them, there's one less there than what's typed in the code because we included the backspace character. Move through everything there with the built-in for each loop, and then the for each loop as a method. I guess I could have labeled those, couldn't I? Labels are good for examples because this is going to go on GitHub in case y'all need to refer to it. So this first one is actually, I'll copy this whole thing. So the first one is a regular for loop. Then the second one is a Java for each loop. And the third one will be a array list for each method. So 3 different ways to do it. This is by far the most efficient for an array list. It's built into an array list, so it's customized for an array list. It doesn't have to be generalized for anything we want to look for. But until you get to really big things, you're not going to see the difference in those optimizations. So at least for now, well, we're in a classroom, so you probably want to use all 3 of them in the classroom, switch back and forth. But in general, you're going to find the one that fits your style best. Find the one that fits your style in general, and then worry about efficiency later. So the order here is improving efficiency, and hopefully it makes sense why the efficiency improves as we go down that list. A generic for loop, a specific for each designed for collections, or the for each designed specifically for ArrayList. There's some of our basic ones, and that's going to act a lot more similar to the list you would have used in previous classes. And your homework assignment this week, you do the same thing twice. Once with actual arrays and then once with linked list and ArrayList. Let's see, so it's coming on 7:15, and I think it's probably gonna be another half hour. So we'll take a short break and then we'll finish up, and then we'll have a bunch of time to actively do stuff after we look at the syntax for linked list. So let's do a little bit shorter break than normal because we're gonna end fairly shortly afterwards. It's just still it would be a long time to talk since we've already been an hour and 15 minutes. So does 5 minutes sound good to everybody? Instead of the normal 10? That'd be enough to run, grab a sip or a drink. Okay, you got stuff to do. So we'll keep it 10 minutes. That works. 7:17, so we'll get back to it at 7:27. And we'll do 10-minute break. Drink a little bit more coffee. So I will see y'all in 10 minutes. Oh, where's the stop recording button? There it is.